I want to talk for a few minutes now about the general mechanism of nucleophilic acyl substitution. So I've redrawn the 4 different carboxylic acid derivatives that we're going to talk about this chapter, and really they can be broken down into 2 parts. The first 2, the carboxylic acid chloride and the acid anhydride, are reactive. They're highly reactive. And they will react with a poor nucleophile without help. And I mean a poor nucleophile like ethanol or water or any other general alcohol. And these 2, the ester and the amide, are less reactive. And they need help to react with a poor nucleophile. And again, a poor nucleophile, alcohols or water. And so that help generally comes in the form of catalytic acid. If we protonate the carbonyl carbon of these compounds, we make them into better electrophiles, and thus they are more likely to react with poor nucleophiles. These 2 compounds, the acid chloride and the anhydride, are already good electrophiles. They do not need help to react with poor nucleophiles. And let's also compare these compounds to what we talked about in the previous chapter, where we can have either an H as an aldehyde or an R group as a ketone. And remember that those are not good leaving groups. So we generally don't do nucleophilic acyl substitution on an aldehyde or a ketone because we're not going to lose R minus or H minus. Whereas if we look at the substituents here, the chloride or the carboxylate leaving group or the OR minus, those are decent to good leaving groups, and so we can do substitution on them. And in fact, if we have enough heat and acid present, we can actually do nucleophilic acyl substitution on an amide, where we turn that back into a carboxylic acid. So let's look at the basic mechanism. And here's our generic leaving group. It's one of the carboxylic acid derivatives. I'm going to react it with a generic nucleophile. And here, you can see that the first step I did was to attack the carbonyl carbon, pushing electrons onto the oxygen, making a tetrahedral intermediate. Let me label that. And then the second step is loss of leaving group. So this is nucleophilic attack, the first step, loss of leaving group, the second step. And you can see that I've reformed the carbonyl, and now I have the nucleophile in place of the X group that I started with. So I've substituted the X group for a nucleophile, and so this is my resulting compound. And this is the general mechanism. We're going to have 2 steps. A lot of students like to condense these 2 steps into 1 step, where they basically show these red arrows, which are not correct. The red arrows are not correct. So they show the nucleophilic attack on the carbonyl carbon and then loss of the leaving group. And that is not correct because we cannot do SN2 reactions on sp2 hybridized carbons. So it's 2 steps. We reform the carbonyl and don't lose H minus or C minus. So you'll notice that I did not do anything to this R group. I'm assuming this is just a standard carbon R group. I did not lose that R group. It was unaffected by the reaction, and that it should make sense because it's probably better to lose a Cl minus or an O minus before we lose an H minus or an R minus. So anytime we're doing nucleophilic acyl substitution, we do not lose the R group or an H that might be attached to it. Some optional steps would be proton transfers. Proton transfers. As I said before, if we're reacting an ester or an amide, we may need to proton transfer first in order to protonate the carbonyl here. If we're using a neutral nucleophile, like an alcohol, as we've seen many times over first and second semester, when you've used a neutral nucleophile like an alcohol, the last step is to remove this extra hydrogen that comes along for the ride. It stays on the ethanol as it acts as a nucleophile, and then we are faced with an extra hydrogen, a protonated product, if you will, and we might proton transfer as the last step to get rid of that extra hydrogen. Also, I'd like to say that under acidic conditions, we should only show cations in our mechanism. Under basic conditions, we should only have anions in our mechanism. So the fact that we have, say, we had catalytic acid somewhere in our mechanism, that's your clue that we should only draw carbocations or oxygen cations. We should not draw any negative charges at all. I like to call those fun with acid mechanisms. Let's look at one example. Let's take a couple of bad examples first, and then we'll look at another good example. So I'm going to do this one in red. This is a bad example. I'm going to react an ester with water and catalytic H2SO4. And I'm going to ignore the acid and just push arrows like this. So you'll see a couple clues that I did the wrong thing. I'm in acid, but you see that I've made this O- right here. Also, my intermediate has opposite charges. And that's going to be okay if we have a very reactive compound like acid chloride or an anhydride. But in this case, with an ester, it's relatively unreactive. And so this is going to be very unusual to make this high energy species from an unreactive ester and an unreactive water. And so we are in acidic conditions. Don't form opposite charges. Unless we have a very reactive, call it highly reactive, starting material. So let's look at a better way to draw this mechanism. I'll use blue in this case because we want to help ourselves remember that this is the right way to do it. And I'm going to draw my sulfuric acid out in a little more detail so that I can draw some better arrows. So we're going to protonate first. If we ever see sulfuric acid in a mechanism, that's your clue that it's a fun with acid mechanism. You should protonate something first. You should not grab the poor nucleophile first. You should always protonate something with your sulfuric acid. Also, don't use the sulfuric acid as a nucleophile. Don't consider it a solvent. It is just a source of protons. So I'm going to protonate the carbonyl oxygen, and that makes the carbonyl oxygen a better electrophile. I'm sorry, it makes the carbonyl itself a better electrophile. I'm going to write that down because it's really important. This is a better electrophile. So now I can take my poor nucleophile, water, react it with this better electrophile in that nucleophilic acyl arrow push that we've been discussing. And I have too many carbons here, or too many bonds here. Let me try that again. And so you'll see that my intermediate now has a single cation, which is fine because I've protonated something with my strong acid. I created a single cation here after the protonation. I reacted that with a weak nucleophile water, and I still have a single cation except that it's now on the O that used to be part of water. So this is great. Gets a check mark. There's only positive charge here. And so this would be a better way to start the mechanism for acid-catalyzed reactions with an ester or an amide. Let's look at a nucleophilic acyl substitution reaction using strongly basic conditions. So here I'm going to draw the same generic ester. I'm going to react that with water and sodium hydroxide. I'm not going to draw the sodium here. Here, I have a good nucleophile, right? Compare that to water, right? I have a better nucleophile now. I do not need to activate the carbonyl compound in order to react with my good nucleophile. So I can just draw this arrow right off the bat. And this intermediate is great. There's no problem here. We are in basic conditions. And that means only negative charges can show up. That's what I have here. So really there's no problem. And then when I go to reform the carbonyl, I don't kick off the carbon species or piece. I would kick off the OR. And that would get me to that intermediate. And again, this is okay. I have not made any cations or positive charges here, so I'm following the rules.